Now that we've defined the pH scale, let's look into some of the calculations involving pH, starting with the pH of strong acids. We've mentioned several times in these videos that strong acids fully ionize in solution. This is going to make our calculations very, very easy. For example, if we have an HCl solution plus water, since this is a strong acid, we're not going to have any equilibrium present, and it's going to be H3O plus aqueous plus Cl minus aqueous. So this is going to be great because for every 1 mole of HCl, we have 1 mole of H3O plus. Remember that our molarity is equal to moles per liter. So the moles of HCl equal the moles of H3O plus, and the concentration of the HCl is going to equal the concentration of the H3O plus. Okay? So if we were asked what is the pH of a 0.10 molar nitric acid solution, we know that since nitric acid is a strong acid, the concentration of HNO3 is going to equal the concentration of H+, which is going to equal 0.10 molar. Our pH, remember, is equal to the negative log of the H+ concentration, which is going to equal the negative log of 0.10 molar. This is going to give us a pH equal to 1. Now, we can characterize strong acids and strong bases based on the fact that they fully ionize. Okay? We can still have a very small concentration of these acids or bases, and the strong descriptor does not mean that the concentration has to be high. So let's do an example of this, and this is kind of one of the trickier questions that you might see involving these types of reactions. So what is the pH of a 1 times 10 to the minus 10 molar HCl solution? Okay. One of the things we have to mention here is that HCl is an acid, so that means its pH is going to be less than 7. But in this particular case, if we look at the H+ concentration from our HCl, it's going to be 1 times 10 to the minus 10. If we took the negative log of that, our pH would be 10, implying that this is basic. But this is not going to be the case. So we have to think of why this might happen the way it does. And here, our H+, we have to consider the auto-ionization of water, which we described a few videos ago. This is going to be 1 times 10 to the minus 7. So when we add these two together, our H+ total is going to be 1.001 times 10 to the minus 7. And we need to keep this into consideration when we're at pHs close to 7. Okay? In the previous example, we had a concentration of H+ equal to 0.10. If we add 1.0 times 10 to the minus 7, we're roughly going to equal 0.10. So we don't need to worry about the auto-ionization of water for really, really acidic solutions or really, really basic solutions. But here we do. And if we took the negative log of this value, our pH is going to equal 6.9996, which is roughly equal to 7. Okay? So don't get tricked here by saying that there's a pH of 10, because we do have an acidic solution. Okay? It's going to produce H+ ions. But we also have to consider the auto-ionization of water, which will give us a minimum H+ concentration of 1.0 times 10 to the minus 7 when we're dealing with acidic solutions. Okay, so these are some examples of some calculations that you will see for pH of strong acids, and this situation changes dramatically with the equilibrium that we're going to see for weak acids, and we will talk about weak acids in the next video.